and John Dallen's Mr. Dallen's Midnight. And I'm going to get into other things. The winter season. This is Reindeer, and I had G sharp down the bottom. I am playing a Lion and Healy Prelude Lever 40 part. So that's why I had hence the levers. I'm going to change this up a notch to the winter. I'm going to have B flat and a C sharp. Okay. sorry. Vivaldi's, one of the Vivaldi's Four Seasons, Winter, an arrangement by Jennifer Eklund. A beautiful arrangement. So that was, okay, so now next up we have Philip Wesley's Carol of the Bells. Let's try Carol of the Bells here. So on my Lion Healy Prelude Lever 40 harp, I have to change the notes using my hands instead of with my feet if I had a pedal harp. So this is called a lever harp. Philip Wesley. Let's see, how am I on time? Okay. Let's see, let me try The Whisper of Winter by Philip Wesley. And I'll be changing this into 3 sharps. So A major or F sharp. Okay, 3 sharps. Oh, okay, C sharp. C sharp, C sharp. And I think it's 7:30. Are you guys still leaning more? Like I did the whole program.
I would go ahead and play some more, Kim.
Oh, you want me to play some more? Okay.
Please.
Okay, I did have something here. Let's see. Oh, okay. Let me just try this one for fun. Let's see. Frosty the snowman was a jolly, happy soul with a corncob pipe and a button nose and two eyes made out of coal. Frosty the snowman was a fairy tale, they say, and inside of stove, but the children know how he came to life one day. There must have been some magic in that old silk hat they found, and when they placed it on his head, he began to dance around. Frosty the snowman was alive as he could be, and the children say he could laugh and play just the same as you and me. Thumpity-thump-thump, thumpity-thump-thump, look at Frosty go. Frosty the snowman knew the sun was hot that day, and he said, let's fun and have some fun before I melt away. Down to the village with a broomstick in his hand, running here and then there all around the square, saying, touch me if you can. Then down the streets of town into the traffic car, and only pause a moment when they
Too
got
much.
stop. Frosty the snowman had to hurry on his way, and he waved goodbye, saying, don't you cry, I'll be back someday. And that was Frosty the Snowman.
Thank you very much, Kim. That was really great.
Thanks, Kim.
You're welcome.
Um,
I thought I had to mention one song with the word sun in it.
Hi, everybody. Thanks again, Kim. I have the privilege of speaking to you all from the auditorium. Can people hear me?
Turn it on. No,
Oh.
not there.
Sorry.
Whoops, you had it on.
That's what, testing.
Oh, no, did you change the channel?
I didn't touch anything.
It's working.
Okay.
We can hear you.
I won't touch anything because it seems it's far more fragile than I thought. Anyway, for those of you that couldn't hear me when I was saying anything before, I am in the auditorium at Chapman University. We have a nice representative sample of club members. It's so great to see people in person here. And I see that they are being careful and keeping a reasonable distance between them so that we do not make this by any means a super spreader event, which none of us wants. Welcome to the December meeting of Orange County Astronomers, our very first hybrid meeting. Before I turn it over to Kyle for the announcements, I would like to remind you that we are in the midst of our very own, not very contentious election season, and please do get your ballots in. The election ends at the January meeting. As all of you know, just in general, things tend to change quite a bit rapidly. I would suggest for those that are planning to come to the January meeting in person, please keep an eye on the website in case there are any changes that Chapman imposes on us. So that, you know, if they have a reaction to what's going on with infections and all that, that they don't want us on campus for a month, you know, that could happen. Anyway, without more ado, happy holidays, everybody. And I think that it's time to hear the announcements from Kyle.
Awesome. Here we go. I'll go to the beginning. All right. So welcome new members.
Kyle,
Sure.
you might want to give it a pause, making sure they have your audio there.
We're up.
We're good?
Yeah.
Okay, awesome. Once again, welcome all new members. Your membership badges should be on the whiteboard there. I think I saw them earlier. So feel free to pick them up. They'll probably be there a month after you submit your application to join, just because that's how long it takes to make the badges. Barbara mentioned about the OCA leadership elections. There's a paper ballot in the Serious Astronomer newsletter, as well as shortly an email will be sent out with the electronic voting instructions. Please feel free to vote either way. If you do not get the electronic voting instructions in the next little bit, feel free to email John Hoot at the email there to update your email, because that could indicate that we missed you or whatever. Just check on the status of those. Voting ends, as Barbara said, at the end of the January meeting. Here are the candidates. Even though it's not very competitive, we always encourage everyone to vote in order to have a vote of confidence and ensure that everyone is happy with the club leadership. So start parties, please check on the website calendar for more information, as those are quickly changing and they may be added on short notice, as well as the astrophysics special interest group meeting is back meeting in person December 16th at 7:30 at the Heritage Museum. Beginners class is also back in person at the Heritage Museum January 6th, 7:30. And the OCA board meeting will be online January 29th at 10:30. And to join the online events, please check the OCA website calendar. We are currently looking for a new outreach coordinator. So if you're interested, please contact Alan Smallbone, as well as if you're just interested in volunteering for the program, feel free to message Alan Smallbone. But do note that the outreach event program is currently on hold until we find a new coordinator. Our speaker for tonight, Tim Hogle, has some free NASA posters. If you are interested in getting one of these, please go, for the in-person attendees, go up to the coffee stand and you can get a raffle ticket there. And just a reminder that if you are in person, there is a coffee stand that sells coffee, donuts, and water. That will be up top by the main entrance near the little library. And those things are available for sale. Before the meeting and through the WhatsApp presentation and then after the main presentation, pretty much just any time when the main speaker isn't talking. The Adopt a Scope program, been mentioned pretty regularly, but again, the new list of inventory is under the Resources tab on the website. Then you can see the adoption agreement along with the current inventory, and you can read more information on that program. If you have any items you'd like to have featured in the Serious Astronomer newsletter, please contact Dave Fisher and he'll review those items. If you would like your Serious Astronomer newsletter to not be mailed to you, again, by default, it's mailed to everyone. But if you'd like to opt out of receiving the printed copy and only look at it online, please email Charlie. And to all members, the Serious Astronomer newsletter is always available online on the website. Please remember to keep pads in the observatory areas clear of weeds at the ANSA site. And if you can help out anywhere else while you're out there, that is greatly appreciated. And the next hybrid meeting, we're planning on keeping it in the same format as this month, will be January 13th. Please remember as of now that due to some insurance issues, only people 18 and over are permitted in person until those issues are resolved. But everyone is welcome online. And then John Garrett will be up next with the WhatsApp presentation. Thank you.
Where are you now? Okay, and that is over on this screen over here. No. All right, so I need to start you, and then I need to share screens. Come on, man. Move this over here. Come on, man. Come on, man. What happened to the meeting? Over here.
So for those of you who are online, we are going to have John's WhatsApp presentation shortly while the in-person crew tries to put it up.
Okay, it's over there. All right. Thank you for letting me be here. I look forward to this.
John, you need to share your screen. We are not seeing the presentation.
This is always challenging. Okay. This is a dexterity test.
Yeah.
And then yeah, I've hit that. Now I have to find the right
Screen. Okay, it would be
not that one. That one.
We don't have it. It's not showing up. Maybe click the bottom right one. And if it's not the right one, I can still use it.
Oops. Ouch.
Okay, something is appearing here.
I hope so, but I'm not sure.
Okay, I see a blank screen, white blank screen.
And that's not what we want.
Oh, that's a whiteboard that you're sharing. I see.
How do I close this? No, now we don't have that. All right.
Sorry, I got sent down here. Sorry to
thank you.
interrupt. If you go back to Zoom, go click share screen.
Well, Zoom is over here.
Oh,
See, this is too many cooks and not enough broth. What I'd like to do. What's up? And the slideshow is running, which is crazy. Yeah, but I'd like to get it over on.
Yeah.
All right, I want to select this. Come on, you son of a. All right, I think I'm sharing that. Now I need to get that screen over to this screen. Now I think that,
so now if you click share screen, see the
Yeah,
green
now.
share screen button?
yeah, now I can get there.
Yeah.
All right. Yeah,
Yeah, right there. Click that.
yeah, right.
And now the what's up. See what's up? No, and go to the right, go to the right, go to the right, go to the right, go to the right. Yeah, click that. Yeah, click that.
That's.
Oh, no, go over one. Go over one. Yeah, right there. Click that. Yeah, click that. Yes. I do this every day. Sorry. And now go down and click this.
That's the screen. It looks
Oh,
like
is that it?
Yeah, this looks like page 2.
Okay, I see an image here, a trail of
Bars, yeah. That's the one we need you to put up if you can get there.
well, we see that. I think it's all shared. That's
Uh,
up.
That's really unfortunate, because no one here can see it.
Oh.
This is,
John, set your screens to just duplicate, not
yeah, I think
extend it.
we need to go back and just duplicate. That's, all right, so, stop screen share and go back out of here. All right, now we go down here and, okay. Oh, I know how to do this fast. All right. Here we go, duplicator. All right, now, all right, we got lots going on here, but I can minimize this because this is not my problem. And we go over here and we start your program again, or is it still running, I guess?
It should be still running.
Yeah,
I was
so
trying to
let's-
page. Oops.
You're on a short leash. I don't think it is running. Now it is running. Okay, and now I want to go over to Zoom, which, and can you share my screen or, oh, hold on, let me,
You
I
have
can
to-
try to request control, but then that doesn't let me
all right, hang on for a second. here.
control Zoom. Okay.
All right, what I'm going to do is I'm going to stop the presentation. And at this point, I'm going to go and share screen. If I go to Zoom, share screen in Zoom. Where's Zoom? Zoom. Where's share screen here? Where is Zoom? This is very annoying. Okay. Here we go.
Okay, you got it.
I got it. All right. Actually, I want to share the screen. Yeah, and then we're going to go big here. Yes, I am trying to screen share. And then,
You are sharing your screen right now. I'm seeing the PowerPoint and it's up now.
there we go.
Let's see if it actually goes back and forth. It does. It looks like we're in business. Hi. I hope the people not here, they're not clapping for me. Yeah, so what's up? 3 weeks ago, I was able to get out in the desert in preparation for tonight's What's Up. And when I got out there, I thought, oh, this is so cool. I just want to share it with people. So that kind of works both ways. So thanks for the impetus to get me out there. And so all the pictures that I took, at least most of the pictures I took that are wide field shots, I took out in Anza Borrego about 3 weeks ago. And I took them at about between 7 to maybe 8:30. So everything that I'm showing you now is going to be what it's like if you get out right at about 7 o'clock or so. So I'm showing you what's in the early evening. It's December, it gets dark early, so you might as well get out in the early evening. And while you're there, that kind of appeals to another quality is that you can get back before it gets too cold. I find this kind of time of year extremely cold. Anyway, so the first shot I'm going to show you is this is where Saturn is tonight. So if you look into the southwest, you'll see a bright star. And then if you look a little harder, you might see the constellation Capricornus. And the bright object in that is Saturn. So Saturn is still with us for maybe another month for good observing in the evening. You'll need a telescope to see Saturn well. And just off of Capricornus is Pisces Astrinus. You might recognize it by the bright star Fomalhaut. It's one of the brighter stars that we have in the sky. And then above all of that is the constellation Aquarius. I've always had trouble believing in Aquarius because I have trouble seeing it when I get out there, but I took some pictures and my pictures line up with the maps. I can look up Aquarius. And so we're, while in that area, there's a number of really nice dark, deep sky objects. Okay, and these are some a few star clusters and some nebula that are in the sky in the lower western, southwestern sky. Over the past pandemic couple of years, I got rather obsessed with planetary nebula, and so for a while I didn't even want to have conversations unless I could work planetary nebula into the conversation. And so two of my favorites are right in this area, and let me show you. Oops. I don't know if you can see that. It's right behind the little bit of pictures. That's M2. M2 is the one up top. I didn't see it. It's right under the got it. That's M2 is a globular cluster, beautiful star cluster. As you can see behind the picture of me, I'd rather you see it than me. I don't know what to do about that. But fortunately, I placed the next one out here in the open. This is the Saturn Nebula. It gets its name from looking like the planet Saturn, but it's a planetary nebula. So that's a good one in a telescope at high power. And the Helix Nebula. This one I took with my 3-inch telescope, and it's probably one of the first images that I've learned how to stack and get a better quality image than you get with a single picture. So that's all in that area. And we go from there a little farther up into the sky. We'll come across to where Aquarius ends and Pisces begins. And right between the two, as you'll find the planet Jupiter. Very bright, you can't miss Jupiter right now. And about right there, you see that little Neptune pop up. That's where I figure in this photograph, Neptune must be. So I think it's one of the little fine points in this photograph. And then off to the left, left is Cetus the whale. And so when I was out in the desert, just those 3 weeks ago, for the first time, I noticed that at this time of year in the early evening, Cetus the whale is swimming horizontally. So that's just one of those note to self, Cetus the whale swimming horizontally. But there's some some planetary nebula and some galaxies in Cetus that was my project that night, and they're going to be my continuing project as soon as I get out to the desert, perhaps a week from now. And so these are the couple galaxies right here near the mouth of the whale, and a planetary nebula just above the whale. And so I was taking some of these pictures. Again, I didn't foresee how that wasn't going to show up in our particular show, but I think this one is NGC 246, a planetary nebula. And this was taken with my 3-inch refractor. And fortunately, the last image I took with my telescope that night was with my Schmidt-Cassegrain. I took a bunch of images with my 3-inch scope, and then I put the first image in my Schmidt-Cassegrain on this target, and I realized my tracking was way off. And you're not really seeing it, but it's showing it really nice on this monitor. Anyway, so a beautiful planetary nebula, and it's almost as big as that little cluster of 3 stars that you see up in the top half of the screen. Again, I'm not seeing it up there for there, so just take my word. It looks like a beautiful planetary nebula to chase down someday. But right now, As soon as it gets, the moon gets out of the way, it's going to be about as high in the sky as it gets for the year. And so it'll be the time to do that. Oh, okay, there you go. Okay, and now you can see that there's a lot of noise in my pictures. I'm not taking great pictures. Most of my pictures, I like to take a single frame with a camera so that I don't spend I can see a lot of objects and capture a lot of objects when I take the drive to the desert. And then other times I've been trying to do a little more of the processing to get better images. But you can see that one really looks like it's worth coming back. And I don't know what that little one is off to the left, lower is, but it's kind of neat that they both end up in one field of view with a telescope. And this one, I believe, is NGC 247, another galaxy showing up nice. This was in my 3-inch refractor and just a single frame photo. And this one is NGC 253. I think it's got a name to it. I think they call it this sculptor galaxy or something like that. But very, very beautiful. And then this one here, NGC 288. And what I liked about this, and you can't see it, is the area. Oh, yes, you can. Up at the very top part of the screen, you can actually see NGC 253. And so after I looked at these photographs, I realized, well, my aim had just been a little worse. I probably would have got both of them in the camera field of view. So I'm going to go back next time, use bad aim, and try to end up somewhere between them as the center point and try to get both of them in my field of view. So anyway, those are objects in Cetus the whale. So Cetus the whale is about as high as it's going to swim for the year. So a good time to look at some of those items. And if we go this way, now we come closer to the constellation Eridanus, the river, and also up at the top, Taurus, the bull, and then Orion rising. And that bright star right there is Mars. And Mars, since the time that I took this picture, has moved almost off the screen here, just right above the Hades cluster in Taurus. But Mars is at opposition. Now is the time to look at Mars with a high-power telescope if you haven't done that already. And so here's some of the famous constellations, the Orion the Hunter and Taurus the Bull. And now if we go this way, first thing you might notice is that I'm photographing a little bit higher and you can see the winter Milky Way. And so the winter Milky Way is this area that I loosely traced. And this is the constellation Auriga, the charioteer, and these stars are the primary stars they use to designate that constellation. And Taurus is over here. Taurus, one of the horns, shares a star with Auriga. And up above it is Perseus, which is, from our point of view, being blocked by some of the user interface controls here. And then here's a whole mess of dark sky objects in that area. And so one of my favorites, of course, M35 over in the lower corner. And here's a M1, which is between the horns of Taurus the bull. This was taken with my 3-inch scope in the city. And then this is one of the, back here, you can see planetary nebula, IC 2149. So to me, this is what I live for, because I'll look at them, they'll look like a tiny little dot. And then maybe with the bigger telescope, they'll look like a green, tiny little dot. And just to see a really green, powerful green object amidst the black and other colored stars, to me, it's pretty exciting. I mentioned that it's early, a good time of year to get out there early because it gets dark early. Here's M35. I took a picture of this at another time when it was still twilight. So M35, that star cluster, is bright enough that you can bring it out pretty well, even with a lot of twilight to work with. And so here's our little constellations again. And now if we go up from there, we go into the area of Perseus. And you can see the winter Milky Way continuing off to that way. Anyway, so here's Andromeda, Triangulum, and Aries. And over here, the Pleiades. And so that's a very distinct and recognizable, not constellation, but asterism in Taurus the bull. And then the double cluster up there above Perseus. And the California Nebula, not an easy object to photograph with the telescope, at least with my methods, but I found often with just a 50mm camera lens where I try to get the nebula and the Pleiades, I could capture them both and they come out pretty well. And so here's a bunch of objects that are in that region. And then over here is where I estimate one of those stars has got to be the planet Uranus. And so I've drawn the ecliptic and I've traced a few stars for me to figure out where, which one's a star and which one wasn't there before. And so I think Uranus is right there. Now, if we go, here's the planetary nebula, M76. So right there near the foot of Andromeda is actually a part of Perseus. but there's they call that the little dumbbell because it resembles the dumbbell nebula. And then here's Perseus, the character, and the character Aries drawn over there. And if I go up a little higher from here, we go to some constellations that are high overhead in the early evening. And I took a moment here to just let you appreciate all the different stuff that you could actually see with a wide field camera. And so you can see M31, M33, NGC 752, M34. And you can even see in that little circle of M30 of 76, a little green dot and another green dot over here in NGC 7662, another planetary nebula. And here's the constellation Andromeda. That's it's often depicted, and there's a characterization of it. And so here is the planetary nebula, NGC 762. You just read that 7662. But this is in my small scope. But in my larger scope, and if I cropped it and expanded it, you can actually get a lot of detail with just a single exposure image. And so it looks like a beautiful target for someone to spend a little more time with. And so moving on from here, oh yeah, there's the constellation Triangulum. And it seems to me a bad idea to let geometric shapes become constellations because it's just too easy. It encourages laziness. And so I'm going to suggest that we rename Triangulum, that we demote it to be a minor constellation. And I'm going to offer something in return. So if you add a few extra parts here, follow a few extra stars, you might start to see a shape of something else form. And so I've decided that that should become James Webbium Space Telescopium. And you can't see it because of the user interface controls, but James Webbium Space Telescopium might be a mouthful to pronounce. So if that becomes a problem, just call it hexagonium. Anyway, so here's these constellations. And then if we move down this way, we come across the constellation Cassiopeia and Cepheus and Lacerta, the lizard. And again, a whole bunch of objects still high in the sky at Cassiopeia, worth looking at before Cassiopeia starts rotate. Let's see, where's, oh, never mind, forget I started that line of reasoning. Anyway, toward the end here, this is going to be the swan song of the wide field shots. If you look toward the west, you may see Cygnus the swan setting this time of year. So there's the last we're going to see of Cygnus for a while. It's going to get lower and lower and lower, and then we'll have to wait till the next summer before we see it again. Now, in this constellation, I took this photo many years ago, and you can see a little meteor over on the right. That's actually my only image of a meteor, the Geminid meteors. So I just want to call attention that the Geminid meteors peak on the morning of the 14th, so night of the 13th, and it's going to be conflicting with a gibbous moon, but it often is a good meteor shower, so it'd be worth looking at if you don't mind the cold. And then, of course, following month, early in January, there's also a meteor shower. I haven't ever watched this one that I know of, but again, a conflicting moon, but also potential for a lot per hour if you are out in the early morning hours. And so, thank you.
Can you hear us?
Yes, well, hang on and we will hear you better. Okay. All right, you're on the air. I'm going to see if we can clean up the display here a little bit. All right.
Sure. I just wanted to thank John for his wonderful presentation and introducing us to the James Webb Space Telescopium, which is better named hexagonium from triangulum. Okay. And I want to let John know there's a lot of kudos coming his way from the online audience. I'll see it all on our screen. And then next is the award ceremony, right?
Yeah, I introduce. Yeah. Okay, so this part is on.
Where do you want us to stand?
You
We need stage direction.
Yeah, you will see your face here. That's going to point at people's navels, maybe. All right, here you go. All right.
Oh, okay. Many of you may recall that one of the real items of pride for our club is that One of our longtime members was honored this year with the award of the G. Bruce Blair Award, which is every year the WAA gives it. And unfortunately, when it was first actually technically given to Tim, who received the award, our very own Tim Hogel, the sound didn't come through too well. So we were not able to play the video of that, even though it was before the 100-inch, which was just a really great backdrop, and so on. So tonight, we have the very great pleasure of welcoming Tim Thompson, who is going to make another attempt, this time hopefully that we can all hear, to give the award. So please welcome Tim Thompson from Western Amateur Astronomers.
Oh boy. Well, I am the current president of the Western Amateur Astronomers. WAA was founded in 1949 with the express purpose of fostering communications and cooperations between astronomical societies. It's a society of societies. And from the early days, I have to look at them, not you. Sorry about that. Don't take it personally. And that objective still goes. And since the early days, we've been awarding the G. Bruce Blair Medal as a Lifetime Achievement Award for someone who has spent a long time, obviously, devoting themselves to public education and amateur astronomy. And this year, we decided to present that award to a very deserving Tim Ogle. It's the night of the Tims. And so it's my pleasure to hand Tim Ogle the G. Bruce Blair Medal, and feel free to show it off. There's the camera.
Sure is pretty. Let's see.
And now it's Tim's turn.
Okay.
I think perhaps before you get started, did you want to give the introduction, Raisa?
No, we're gonna.
Just go straight through?
do it.
He still has to accept.
I have to accept the medal.
You didn't get, you want to give it back? No.
No.
Okay.
Now that I've
No.
got it.
I will protect.
Yeah, so without going into too much detail here, I've been associated with Western Amateur Astronomers for some 40 plus years, and as club representative for OCA, as well as currently vice president of the organization. And so I've been involved with the voting for the G. Bruce Blair Medal for a very long time. And it never occurred to me that people might think that I was deserving that award. I was just kind of plodding along, doing what I enjoy doing and providing service for astronomy here. But when I was nominated by the Orange County Astronomers, I always rejected the award because I thought, that's not me. This is for really people who have really done something. But I realized that
Oops.
I was kind of blown away. It was just a very emotional experience for me. And I am delighted to be able to accept this. I will say as a follow-on to that, what I've done is things that any of you could have done. And I'd encourage people that might be listening to get out and volunteer to do things for others in amateur astronomy, further the cause of astronomy, help do outreach, just bring your telescope out and show other people, maybe get a job at JPL driving spacecraft. Okay, that helps. But share whatever you're doing astronomically. And you may not get an award for it, but the satisfaction you get from doing that sort of outreach work is really very much the reward in and of itself. So thank you very much, Kim. So I guess the presentation is next. I'll have it back to you. A brief moment here while we bring up Tim's presentation.
Well, actually, if you can have me on the screen so I can introduce him, that would be better.
Oh, I put you on the screen. You're on our screen.
There's a little raise. You want a big raise?
Yeah, make yourself large. You're on the big
Okay.
screen. It's showtime.
Let me.
Well, now you're not there.
Oh, that's me. Okay, there you go. There he is.
Okay.
We're really not trying to get rid of you. There you go.
Okay. Is my sound coming off of the PA system all fine?
Yes.
Okay, so hello everybody. My name is Reza and I'm the vice president of the club. I too would like to welcome you to this general meeting of the Orange County Astronomers on December 9th, 2022, our first in-person meeting since April 2020. Our speaker at this meeting joined JPL a few years after getting his degree in electrical engineering from Cal Poly San Luis Obispo, when Voyagers were just launched, where he became a member of the flight team. He started as a real-time analyst, seeing the data coming in before anybody else saw it. More than 27 years later, when he was retiring, he was involved in nearly all aspects of the mission, providing his expertise to help extend it as long as possible. I'm truly pleased to ask you to join me in welcoming one of the people who about 60 years ago helped found this fine organization that we are members of, Tim Hoggle.
Let's see if I can. All right, so. More stuff to get rid of. Okay. Let's do this. Okay, and always fun and games. Okay. And can't do this in the right order. And start that. There. Go.
Okay, we have the presentation on.
All right.
You're up. Okay, we're not going to be able to get rid of the analysts there because I think it may overlap some of my slides.
You probably will for this audience. The online people don't see that
Oh,
because this is the host machine at the moment. And so I have the same problem. I can never see my slides.
Here we go.
yeah.
There we are.
Oh, yeah. I love it.
There you go.
Okay, now, can you guys in the online see me?
Yes, we could see.
Okay, online, great.
They see your slides.
Click myself in here and now I'm not able to move. So I can drive spacecraft off to the far corners of the universe, but I can't set up a computer to be able to show two images at one time. So thank you, John, for getting this started. It's well beyond my technical capability to do that. Anyway, I am very delighted to be able to be with you tonight to talk about my very favorite subject. Now, John, this on here does not include my speaker's notes, which I'd kind of like to have.
Oh, you got to wing it. I think
Reason
you
you're
know
right,
the
I should have printed my
subject
speaker
really.
notes. Well, I do have some things I wanted to say from that. So you don't think you can fix that? Is that? Okay. We'll see how this works then. Anyway, I am glad to talk to you about the Voyager project. It's something that I was involved with for 27 years, and it was really the greatest career that I can possibly imagine. I'm going to give an overview of the mission here tonight, but I'm also want to particularly impress on you 3 points, which is where the spacecraft are now, how they managed to get extended from an original design of a 4-year mission out to 45 years now and counting, and where they're going in the future. So as we look at, this is supposed to be mission overview. This all started back in the early 1960s when a graduate student named Mike Minovich managed to solve the special case of Newton's 3-body problem, the 3-body problem of Newtonian mechanics, and this was a particular solution that allowed us to be able to send spacecraft from one planet to another using the gravity of the first planet to be able to get to the second one. Let's see, John, you don't think you can get to me the notes because I'm kind of dependent on my notes to a certain extent here.
It will make your presentation small.
That's okay. I don't care if this presentation is smaller. I just like to see my notes. Okay.
Yeah, there are your notes.
It may be that you guys get to read my notes before I get to say them, but it's better than otherwise. So yeah, we'll go back to this second slide here. It's not.
Now you use the backspace. Okay. Too many buttons.
This is the first one. Yeah.
Now you can go through here and you can scroll up and down.
All right.
All right. So.
All right. My.
So you want to get in the 3 bodies?
My animations won't work with this way, but that will work. So anyway, we'll go back up here to where we were. Anyway, I mentioned that.
Are you changing slides? We are not seeing, we are just stuck in the beginning, one view. It says mission overview in the beginning, the grand tour.
The one that I am looking at right now. Is that the one you're seeing?
We do not see no notes. It's just says mission overview in the beginning, the grand tour opportunity discovered.
That's wonderful, because that's what I want you to see. Now,
Okay, perfect.
anyway, a few years after this, in 1965, another student who was working at JPL identified one of these paths that allowed the gravity assist technique to be used that could provide for a path to go by all of the giant planets, Jupiter, Saturn, Uranus, and Neptune, in a 12-year mission. And the next launch opportunity was in 1976 to 77. So they need to get started because this alignment only happened every 175 years. And so the concept of a grand tour was open. Do you see the one in the beginning, the grand tour opportunity discovered, Riza?
Yes, we just see the first one. Is there a second line showing now?
There will be here.
Okay.
Does that show a second line?
No, I'm not seeing a second line.
Okay. Well,
Yeah, I'm seeing, I guess we are on something static right now.
Let me,
Can John stop sharing and reshare?
yes, that's exactly what we're going to do here. Stop sharing. We are going to now actually close the presentation proper. And then we're going to share that screen. And this will go away. And now I believe when he advances, it just advanced for you, right?
Right, right. So I guess we are with the notes because we need to have the notes, that's the view we're going to see. Yeah, right. So yes.
you see the notes, then I don't see them. Okay, so first one, we're down here to the mission overview. Do you see a full screen here or just the first line?
But I see a thumbnail of slides. I see notes and then the main slide.
But the main slide is a full slide with 3 bullets?
Yes.
Okay, all right, that's the same thing we're seeing here. All right, so my animations won't work, but that's a very minor thing. So this 12-year mission to the outer planets, that was considered inconceivable because in those early days of spaceflight, missions usually lasted only hours to days. And so a 12-year mission seemed like a technical impossibility to the powers that be. And it certainly would have been exorbitantly expensive to try to build a spacecraft that would last that long in that time period. However, some people did keep pushing on NASA and finally negotiated with Congress to provide to get approval for a 4-year mission just to Jupiter and Saturn, using 2 spacecraft for redundancy, so that if one broke, the other one is still going to go there. And Uranus and Neptune were left as completely unfunded and unplanned options that could be used if we made it that far. No one believed that the 12-year mission would be possible except some of the engineers at JPL, who were then able to provide a few critical resources to complete the 4-year mission. And let's see what happens if I try to go down. So we're looking at the trajectory slide. Is that correct, Risa?
That is right. We have that.
So well, let's look at this trajectory. And I don't know if, yeah, you should be able to see my cursor here.
We do.
Trajectory is the original plan. Both spacecraft would be launched in 1977. They'd arrive at Jupiter 2 years later, 4 months apart now, because Voyager 2 is going slower than Voyager 1. And they get to Saturn 2 years after that, separated by 9 months. The plan called for a close flyby of the satellite Titan, Saturn's largest satellite, and the only satellite in the solar system known to have a thick atmosphere. That was just as interesting to NASA as was Saturn itself. And so, but to go get a close flyby of Titan required going underneath the south pole of Saturn, which would then push the orbit or the trajectory of Voyager out of the plane of the ecliptic, out of the plane of the planets, and no more planetary encounters would be available. Now, one of the things that since I didn't have my slides earlier, I wanted to particularly emphasize or just kind of demonstrate how far the Voyagers are away. Voyager 1 is out currently at 160 AU, astronomical units. That's the distance between the Earth and the Sun, the nominally 93 million miles. So Voyager 1 is 160 times as far away from the Sun as as the Earth is. And Voyager 2 is 135 AU. The time it takes to get a signal to or from the Voyagers is 22 hours for Voyager 1 and 18 and a half hours for Voyager 2. To put that in perspective, the outer planets, Neptune and Pluto, and I still consider Pluto a planet, are about 30 astronomical units. And so Voyager 1 is over 5 times farther away than the furthest planets, and Voyager 2 almost 5 times as far. So that's kind of just catching up a little bit. But we'll go on to the next slide here. And I think, there we go. The main reason why Voyager was able to extend so far beyond its original 4-year mission was due to several design firsts that were used for Voyager. Previous missions used X-band as the radio downlink source, but X-band, different frequency, is much more of a long-range communication capability. And so they did use X-band for primary on Voyager. These fully reprogrammable flight computers, and I presume, Reza, you're seeing the whole page, is that right? 5 bullets?
That's right. New technologies.
Yeah. And these fully reprogrammable computers allowed to making changes during the mission. It seems that for at least the flight data computer, you need a completely different program for the Earth to Jupiter phase, for the Jupiter encounter phase, for the Jupiter to Saturn phase, the Saturn encounter phase, et cetera. Each one of these phases require a completely different program. And for the other computers, a lot of modifications for it. So not having that full programmability would have been very seriously detracting from their ability to continue on as they've done. I mentioned here this Reed-Solomon data encoder. It's kind of a technical issue, but the data needs to be coded before it comes to error corrected, coded as before it comes to the ground. And the old method of coding was much less efficient, or was fairly inefficient. It's a 1 bit of data coding to every bit of data. So half what you're getting down the ground is data encoding. Reed-Solomon reduced that to about 15% for code. But the problem was, even though they could easily make a Reed-Solomon coder and put it in the spacecraft, decoding it was an extremely mathematically intense proposition, and no computer on the Earth at the time of Voyager's launch was able to decode Reed-Solomon data. What they did is they assumed that by the time we needed it at Uranus and Neptune, they would have developed that capability. In the meantime, the old-fashioned coding was used for Jupiter and Saturn. There was also a dramatic improvement in our ability to handle problems and failures that might come up without waiting for ground control by putting fault protection, fairly substantial fault protection on the spacecraft. And as I mentioned, the normally redundant flight data computers were able to be used in parallel, which I'll get to a little later. And let's see here. Okay, science. There are 11 experiments on the Voyagers. These first 4 bullets here are remote sensing instruments. They could be pointed. There's actuators that can move it back and forth and up and down to point at the planets and their satellites as desired. The last 6 of these are fields and particles instruments. They basically make measurements of the conditions around the spacecraft itself. And the asterisk instruments here are the ones that are still operating today. The single asterisk plasma detector indicates that it's only operating on Voyager 2. I want to say, because since I'm talking to astronomers, I wanted to say something about the cameras. They used old-fashioned video camera, Vidicon TV cameras in a single frame mode. And the actual camera optics, the wide angle camera is a 200 millimeter f3 with a 3-degree field of view, and the narrow angle camera, a 1500 millimeter focal length f8.5 with a 0.4 degree field of view. The basic spacecraft configuration that delivered these instruments out there to make those measurements was powered by radioactive thermoelectric generators, radioisotope thermoelectric generators. Those are just nuclear reactors that use plutonium as a heat source and thermocouples to convert that to electricity. They started off at about 470 watts, and they're now down to about 225 watts output just due to the plutonium decay. The spacecraft is a 3-axis stabilized attitude control system, and it is it uses hydrazine as a propellant, monopropellant hydrazine. It's just a gas that is burned in these little thrusters and little tiny puffs to keep the attitude or the spacecraft. It's not its attitude. It doesn't have an attitude, but keep the orientation correct at all times. We also have sun and star sensors on board that maintain the references for the position in space and gyro control for maneuvers. There are also 3 special purpose computers on board, attitude control that does handle the thrusters and the gyros and the sensor star and sun sensors, which is involved in maintaining pointing at the Earth, and the commanding, as well as pointing the science instruments, these remote sensing instruments I mentioned. The command and control computer receives commands from the ground and issues instructions to the rest of the spacecraft. The flight data computer controls the science instruments, and it gathers all the data from all the subsystems on board and formats it for sending to the ground. Telecommunication, I mentioned we do have X-band as a primary for downlink. It operates in a low power mode at 18 watts and 26 watts output, which is still receivable by our big antennas at the Deep Space Network. S-band was a secondary transmitter and is no longer used. We also have an S-band receiver on board for receiving commands. And I'll just go over the highlights of the spacecraft itself. Most prominent here is this 12-foot diameter parabolic dish that maintains up and downlink communications both ways. The Earth is always out here. It's always pointed at the Earth unless we're doing a maneuver that is away from Earth point. Out here is this long, spindly fiberglass structure that is actually just a boom that is holding the magnetometers as far away from the spacecraft as possible so that the spacecraft won't interfere with the magnetic field measurements they're making. Down here is the RTGs, and as far away from the RTGs as possible are the science instruments over on what we call the science boom here. The fixed instruments that are here, the fields and particles instruments, and the movable instruments, the remote sensing instruments, are here on this platform that can be rotated right and left and up and down to point at their targets. The main body of the spacecraft down here contains all the computers, all the transmitters, receiver, the heaters, and things that are needed to make spacecraft work. Right here, you can see the spherical tank is to hold the hydrazine used for attitude control, and for trajectory corrections. And the various thrusters and sensors and things are scattered around the spacecraft. But I want to point out right here is especially interesting, the Voyager Golden Record that has gotten a lot of notoriety. And that's just in case some alien civilization should happen to find the spacecraft, they can pick up that record and easily see that what it says is the sounds of Earth. So very easy, they know what to do with it. But just in case they don't read English, the cover of the record is included with instructions in some kind of supposed universal scientific language on how to play the record and what you would expect to see. The first picture is just a circle if they get it right. And then there's also a diagram here showing where the Voyagers came from, the sun being at the center and direction arrows to nearby pulsars. Voyager wasn't the first spacecraft to visit Jupiter or Saturn. The Pioneer 10 and 11 spacecraft were much more primitive spacecraft. They didn't even have a camera. They just were able to put together simulated pictures from some of their photopolarimeters. They called it imaging photopolarimeter, I believe. In 1973 and 1974, they provided good data to improve Voyager's design, particularly in recognizing they needed a lot more radiation hardening at Jupiter than was anticipated. And it gave us an intriguing hint of what was to come. So it was off to Jupiter. I think I missed the launch months, but just say it was a perfect launch for both spacecraft on their way to Jupiter. And as they came closer and closer, we could start seeing these massive storm systems that were just awe-inspiring, and we got new insights, new surprises, and new questions every day. And the closer we got, these churning and swirling atmospheric storms left everyone speechless. No one imagined the dynamic roiling atmosphere that we were seeing. We're seeing the satellites Io and Europa in front of Jupiter here. And they're beginning to show themselves as real objects, real bodies, rather than points of light. And the closer we got, the more and more confusing the details became until they sorted it out. Until finally we got down to where we're looking right into the eye of the largest and longest living storm in the solar system, the Great Red Spot, which is as wide as 3 Earths side to side, huge. And see, then here's a real surprise nobody expected. The satellite Io, tiny little satellite, looking like a 3-week-old pizza sitting there going in orbit around Jupiter. Nobody expected anything like that, and nobody could make any sense of it at all. This just didn't seem realistic in any way until a navigation picture showed this little blip on the edge, which they fairly quickly recognized was a volcanic plume. And this showed that Io was actually being constantly resurfaced by erupting sulfur from dozens of these plumes around the planet. As this close-up showed, we could see a actual caldera and sulfur flows coming out of that, and this was just exploding all the time on the surface. And then there was Europa, with its icy surface as smooth as a billiard ball, but yet crisscrossed with what appeared to be giant cracks. Didn't know how that happened, but it had to wait for the Galileo mission a few years later to get a real analysis of that. Ganymede is the largest satellite in the solar system, showing here a varied terrain indicative of a violent past pockmarked with more recent craters. And then Callisto, completely saturated with craters. There's no original surface visible here. You just have craters on craters everywhere on this satellite. There are many more observations, many more satellites, but I'm moving on to Saturn. And as we approach Saturn, the rings began to look more and more intriguing. Now we're starting to see details, not only of the rings and their gaps and shadows of the rings on the planets, but also the satellites themselves. And we have here Tethys and Dione are 2 of the satellites right here. At close approach, Saturn was a little more subdued than Jupiter, a lot more subdued than Jupiter's because of high altitude haze. But the rings are what really stole the show at Saturn. See the rings and these micro gaps in the rings projecting their shadows onto the surface, which proved that the rings are very thin. In fact, the rings are 175,000 miles in diameter and less than 300 feet thick. That's pretty amazing. We never ran out of increased resolution at Saturn, and always seeing successively finer and finer details. Titan was, on the other hand, a bit of a disappointment because, I say not disappointment, maybe a letdown. We had hoped that we'd be able to see surface details that would show some analogy to the Earth's surface because of the thick atmosphere. But unfortunately, Titan was covered with a very thick photochemical haze, a very smoggy day all the time on Titan. And it required waiting until the Cassini mission arrived years later to penetrate this to the surface. And of course, Voyager data fed into Cassini's design, and that helped them know how to design those instruments to get down to the surface. One of the big shockers at Saturn was this tiny satellite Mimas, which had a huge impact crater on one side that was undoubtedly almost big enough to smash Mimas to pieces, but had not. It was apparently absorbed and the things held together, as you can see by the uniform surface. But 3 years before this photo was taken, the first Star Wars movie was released, and there was an uncanny resemblance between the Star Wars and this damage to Mimas that almost did it in. And so Voyager 1 took this farewell shot Saturn as it left Voyager 1. And this was, of course, Voyager's last planetary encounter, because going under the south pole of Saturn and coming up to the north meant there were no more possible planetary encounters. However, if you look back at the trajectory slide, now we could consider the red trajectory. And it turned out that they decided that the team in NASA decided that there was no more data that could be gathered at Titan by Voyager 2, no more with a close flyby. And Voyager 2 was seemingly healthy enough to make it for another 5 years to get to Uranus. And so they decided to retarget, before it got to Saturn, they retargeted Voyager 2 to miss that close flyby and that South Pole flyby, stay in the ecliptic, and move on to Uranus, and then eventually on to Neptune as well. So, as I mentioned, Uranus and Neptune mission were not planned before launch. So all the mission planning and verification had to be done on the fly between Saturn and Uranus. You had 5 years to do it. It was actually quite a busy time. Since Saturn is at 10 AU away, Uranus is at 20, and Neptune is at 30. This distance required some spacecraft and ground data system enhancements in order to be able to maximize our data return. Without these improvements, the data rate at Uranus would have been 1/4 that at Saturn. Also, the light level at Uranus would have been a 10th or 1/4% of the light level at Earth. And the Neptune light level would be 1/10% of that at Earth. And so that required long exposures of up to 30 seconds, which the cameras really weren't designed to take photos that long. These required previously untried changes, but Voyager 1 was available to validate this, try them out first before they tried them on Voyager 2. Let's see here, spacecraft. One of the first of 3 major improvements or enhancements they did was image data compression. I don't want to get too much into that, but image data compression was to make the data come down in fewer number of bits than would be required with full frame data. And I'll leave it at that unless there's a question later. But it was a much more efficient way to get it down, but it required a lot of number crunching on board the spacecraft. So they used the backup flight data computer to do the number crunching for the data compression, and then the regular primary computer to do its normal job. The third one is development of a image motion compensation capability, which allowed them to move the entire spacecraft to compensate for the motion of the spacecraft going 35,000 miles an hour through the system, and the actual satellites and the planet moving in their own orbits. It's the same idea that we use clock drive for in our telescopes to compensate for the Earth's rotation, but a more complex calculation, of course. Let's see here. The ground data system had their own enhancements to enlarge the 64-meter DSN antennas to 70 meters, provide for arraying of 2 or more stations. In fact, they included in those arrays at the near encounters for Uranus and Neptune some major radio astronomy telescopes in different places in the world, including a very large array here in New Mexico, and one in Australia and another in Japan. They also installed higher sensitivity receivers, upgraded the command system, the computer systems, and they were able to make a special purpose Reed-Solomon decoder, the first ever had been made, that supported Uranus. By the time it got to Neptune, Reed-Solomon, the computer technology could handle the real-time conversion. They didn't need the special purpose computer. Since then, computers have only increased in capability, and nowadays Reed-Solomon coder and decoder is included in every cell phone and CD player and DVD player that we use and perfectly well take for granted. All of these upgrades resulted in about the same data return at Uranus as at Saturn, even though it was twice as far away. this was not supposed to show, but because of what, these are just some of the antennas that were included in the array. So let's look at the trajectory going through Uranus's system. Uranus is a rather strange body in that its poles are aligned more or less with the ecliptic, in the plane of the ecliptic that it's going around the sun. And so the trajectory for Voyager was to go right straight through this like a bullseye, which meant that all of the targets they were looking at, all these satellites and the planets, would be having their highest resolution images all at the same time. And that provided for a very busy near encounter. Notice in particular this very close approach from Voyager to the small satellite Miranda. We'll look at it in a minute. Uranus itself was not visually very interesting, although there was a lot of good data from the various instruments. Learned a lot at Uranus. The right-hand view is a visible light view, which we could see it covered with the high altitude haze and no detail. The one on the left was an attempt to try to pull out some amount of detail by stretching that view electronically. Mimas, as I mentioned before, was very interesting, got very high resolution views of it. And it seems that Mimas showed very clear evidence of having been broken up by probably a collision in the distant past and then reaccreting in a kind of random fashion, leaving these very jagged and different terrains. These here were probably interior layers of the satellite prior to that impact. And it left even things like this 19-mile high crater, very jagged. Uranus also has very thin, very narrow rings. These were only discovered a year before Voyager was launched. They're black as coal and very hard to see. They could only see them from the Earth using star occultations going behind them. That was how they were discovered. But with Voyager, we could look back towards the sun and see the rings in forward scattered light, and they were very easily visible. Let's stop just a minute for the Neptune. This is a slide that I'm particularly proud of because I had quite a bit to do with this. But the Neptune trajectory required the most precise navigation celestial navigation task ever attempted then and probably until now. You had a spacecraft coming in from the right at 40,000 miles per hour. It needed to arrive at a point 2,000 miles above the cloud tops at Neptune's north pole. And Neptune is, of course, moving in its orbit. And they had to arrive there. It was 3 billion miles away, so we had to estimate that in advance. This is 4 light hours away in this time. And they had to arrive at an accuracy of 50 miles in 10 seconds in order to be able to have the proper orientation for the Triton flyby only 5 hours later. No chance to make any changes there. If they had not arrived at within those boundaries, the cameras would have just taken pictures of dark sky instead of Triton itself. But amazingly, we managed to pull that off within 1 second and 22 miles. That was, it sends chills down my spine to even think about that. So as we moved in on Neptune, we could see that it also had high altitude haze, but not enough to obliterate the features like it did on Uranus. And we were able to see a lot of the major features. This one here is a roiling storm, much like the Great Red Spot on Jupiter and similar in size. And it was dubbed the Great Dark Spot, kind of in synchronicity with Jupiter's red spot. And others like this smaller one called D2 down below also showed a lot of interest. This persistent white cloud here was zooming around Neptune at 7,800 miles an hour, or 780 miles an hour, something like that. And they called it Scooter because of its speed. And as we approached further, we could see it had pictures that showed high altitude clouds that were projecting their shadows down on the cloud tops, so showing in relief some beautiful views of Neptune. And it was all worthwhile. Here we have wonderful pictures of Triton, some varied terrain, different kinds of terrain here. And it's the coldest place in the solar system, 38 degrees above absolute zero. And yet we saw cryovolcanism active. There were two volcanic or geyser plumes, if you will, of nitrogen coming out of the surface. And I have a little video here that is a video made by three photos of one of these plumes, so you can kind of see it if it works. And we'll just see if it happens here. Yeah, here we go. We can kind of see I'm going to pause it for just a moment. There's a hole down here, a source. A geyser coming up from that source. There's a cloud trail that is, because of very thin atmosphere, is being blown downwind on the surface. And then there's a shadow of this, and you'll see all of these as the video continues here. Amazing that you can have volcanism at 38 degrees above absolute zero. And so spacecraft have done everything they expected to. So now what? We had done far more than was expected, in fact. And they managed to complete the 12-year mission with 30% of the original propellant remaining due to some changes we made earlier on to help keep that. We'd had very few component failures. All had been handled by backup units. It looked like a very reasonable 160 bit per second downlink could be expected to be maintained past 2030 and higher rates earlier in this time period as well. Our RTG performance was better than expected. And there were these theoretical targets out there called the solar wind termination shock and heliopause, which were something that the field and particle instruments on board the spacecraft would be ideal for making measurements on. So NASA approved the Voyager interstellar mission, a 5-year extension with possible 1-year follow-ons. And of course, new mission, new flight data programs, a lot of enhancements. The one thing they did for us on the operations team is they finally gave us a new command and telemetry system, replacing the 20-year-old system we'd been using before, which was actually designed for the Viking mission in the early 1970s. And we modified the onboard fault protection to accommodate the longer round-trip flight time that would now be looking at up to a day long. As I mentioned, Voyager 1 is out 22 hours away. And that's because we couldn't expect to be able to handle emergencies from the ground. It would just take too long, be too late by the time the ground responded. DSN has continually added new antennas, allowing for increased arraying capability. They are now using up to 4 DSN antennas simultaneously in arrays to maintain that higher data rate of 1.4 kilobits per second when they need it for playing back high rate science data. Another recent addition was a thermal modeling tool. It may not sound like much, but this allows prediction of temperatures where there are no sensors on the spacecraft. It helps us to gain confidence that the hydrogen attitude control propellant won't freeze in the lines under different power sharing and power reduction scenarios. And we also increased our contingency preparation because we anticipate that eventually in this long extended mission, all the original personnel who had experience from the original mission would retire or move on. The replacements wouldn't have experience in dealing with problems. We had to have that preparation for what might happen. So let's take a look at this heliosphere thing. Heliosphere isn't really a sphere. It's more like a big parabola or a windsock. And it has the sun at the center emanating the solar wind at about 1 million miles per hour. And that solar wind then loses its strength, or the pressure that's created by loses its strength eventually until it balances the pressure of the slower solar wind material out here in the heliosheath, which is that region between the region of active solar wind and the interstellar space. And there's a shock wave there. It's called the termination shock, been dubbed that. And then further out is what they refer to as the heliopause, the edge of the solar, edge of the solar system, or the edge of the heliosphere. Outside of that, or I say at that boundary, the sun's magnetic field basically gets balanced by interstellar magnetic fields and is just gradually turned back into this long wind shock effect. And these solar wind particles are kind of carried along with it. So that outside of there is pure interstellar space. And that's where the Voyagers are now. This picture is a little dated, showing Voyager 2 still inside the heliosheath, but they're both outside. And the final boundary would be this bow shock, which is caused by the motion of the sun going through the interstellar medium and this opposing solar winds from supernova explosions in the past coming in this direction. There would be a shock wave out here. All these constructs were theoretical at the start of the interstellar mission, but the Hubble Space Telescope has shown that these structures are common throughout the galaxy. Here's one bow shock that's shown in front of a protostar in the Orion Nebula M42 from the radiation from the trapezium stars at the center. So finally success. After 14 years and several close brushes with project cancellation due to lack of results, we finally succeeded with Voyager 1 crossing the termination shock at 90 AU in 2004, and followed by Voyager 2 3 years later, then Voyager 1 crossing the heliopause and into pure interstellar space in 2012, with Voyager 2 being a little slower at 2018. And since then, they've been studying interstellar space, totally new environment. So what is the future going to bring? Well, right now, our biggest concern is the RTG output, that is the power output from the RTGs, or more specifically, the power margin, which is the difference between the electrical power that the RTGs put out and the amount of power that's required to run the spacecraft. And that's currently nearly zero. Voyager 1 has had, last month when I checked, about 5 watts positive power margin, and Voyager 2 about 8 watts. And the RTG output is declining due to plutonium decay at about 4 watts a year. So sometime probably next year, they're going to have to make a decision about what to do. And their choices really are twofold. They can either start turning off science instruments one by one to gain more power margin, or they can find a creative solution or both. The creative solutions, and I want to say, there's a caveat here, this is nothing official here. This is just what I'm seeing their options are from knowing the spacecraft. It's not because they're planning to do that, the team is not necessarily planning to do one of these others. I think they are considering what they want to do, whether it's to start turning off instruments or some creative solution. But just to give you an idea of that, either they can allow the voltage to drop below the 30 volts that it is normally regulated to be supplying to the spacecraft, which will cause the entire spacecraft to gradually cool down. Or they can start turning off additional heaters. We're down to where we consider the heaters that are on are necessary to keep the spacecraft at a proper operating temperature, but they may be able to find some that could be, with some additional risk, turned off. And I wanted to stress that any options they try from now are things that the spacecraft is either never designed to operate in, or they was specifically designed not to operate in those modes. And so there's a bigger risk than we've had in the past that propellant could be freezing in the lines. And that is the biggest risk, that we could have hydrazine freezing in the lines between the tank and the thrusters, which then would cause the thrusters to not work, and we'd lose attitude control, spacecraft would tumble, and that would be into the mission. But if it's successful, they might actually be able to get another 5 to 10 years, something that was never envisioned. They really had thought 2019 was the end as far as they could push these spacecraft. And then it was extended to 2021 with additional work. In fact, some of the work I did showed that the RTGs were good till 2025. And then I considered, this is back when I was on the mission, I considered that we might be able to do some of these other things beyond that. But there will be eventually an end to that. We could gain another 5 to 10 years using both of these techniques, turning off instruments and some of these creative ideas. So what does the future hold beyond that? Eventually, a hardware failure, a freezing of the propellant lines, or the last instrument to be turned off will define the end of the active mission. Then the spacecraft will go silent, and the final Voyager mission will begin. There's an interstellar memorial to the society that launched it. The contents of the Voyager record will be a time capsule that will likely outlast us here on the solar system. As these 3 slides I have here that Chris Bartler provided for me very kindly to illustrate this, the sun is now conveniently located at the center of the solar system, warming us nicely like a friendly campfire. But in a few billion years, it'll burn up its hydrogen core and expand to a red giant, engulfing all of the inner planets out to Mars and frying the Earth to a crisp, destroying any vestige of past life. Of course, there's earlier risks to life on Earth. We have climate change on us right now. There are undoubtedly future ice ages to deal with. There's a possibility of large asteroids impact, irreversible poisoning of the planet. Solar instability will start in a much shorter period of time than the billions of years. And there are a variety of other things that we could think of as doomsday scenarios for the Earth. But the Voyagers will be safely beyond all that. They'll be outside, way outside of the solar system. And it's very unlikely that, although it's very unlikely that any extraterrestrial civilization, if any exist at all, which I am doubtful of, will find the Voyagers, but they will be out there in an unending journey around the galaxy. Each spacecraft will pass within a couple of light years of some identifiable stars in the next 50,000 years, but no close flybys at all. So that's the Voyager story, and I'm glad to take questions. We need to change screens and stuff out here. Lisa,
Thank you very much, Tim. Can you hear me?
I hear you just fine.
Okay, wonderful. Thank you very much for this great talk. Much anticipated. I was looking forward to this talk early on when I joined this institution more than a decade ago. So let's get with the questions. There's a lot of kudos coming your way from the online audience. I don't know if you could see them or not. But the floor is open for you to ask your questions. The online audience can send that via the Q&A button, and then we'll have some extra time for the in-person questions. So let me get started here. We already have some questions. You did mention briefly about the fault protection systems. Can you tell us more about that for the uninitiated? What kind of faults does it protect? A little bit, how does the spacecraft do it, and what changes were made?
Yeah, this is for any. Let's see. Can you hear me now? I guess.
Yes, all of it.
These are routines that have been programmed into the flight computers that, in the event that something fails, that a failure indication comes up, they will be able to sense that. There are certain sensors that, for example, one example, if a transmitter were to fail, there's a sensor on board that would be able to tell it, oh, the transmitter output just went to 0 and the transmitter hasn't been turned off. It tells this routine through a mechanism, electrical signal, that this happened, and the routine will go through a sequence of switching hardware, switching the transmitter, switching other components to try to get that back online, switch to a backup. We do have 2 transmitters, and in fact, 2 of everything but the read, column, and coder on board. And so if these happen, it would do that switch automatically. If we had, for example, as we did have early in the mission, one of the receivers failed on Voyager 2. And if we have a receiver failure, that means you can't get commands into the spacecraft unless there's an onboard routine to switch receiver, to recognize there's been a receiver failure and to switch to the backup receiver. And that's what happened with Voyager 2. There are other things that if one of your attitude control thrusters were to freeze, or not freeze, but fail, I should say, then the fail open or fail close, then you would see the spacecraft start to drift off point, and the sun sensor and star trackers would, in whichever axis the failure occurred, would start to see that they weren't able to maintain that attitude control. And so on board are routines that if they start getting a large error in attitude control, the attitude control computer will initiate a program to switch to backup thrusters. So that's the kind of thing that they're doing with fall protection.
Thank you. And just a few technical things. Can we have the light in the auditorium on so that we can see you? And also, I don't know if the question was heard by the audience there in person as well.
The question, I think it was. Did you hear the question for the last question? Yes, we heard.
Okay, perfect.
You just fine, and you spoke the question. And as far as
Okay.
I have to let somebody else deal with that.
And here are a couple of questions more. So are the star trackers still working?
They have to be. They can't maintain the pointing at the Earth and knowing our orientation for the science instruments without the star trackers. But it's a good point because all the star trackers on board have suffered a lot of degradation over the years, but they are still fully functional. That's good, right? Can you see me now?
Yes, all good. Thank you. Next question is there a compendium somewhere of lessons learned from this program? What kind of success should be emulated?
You know, that's one of the things that I really fought for while I was there, is keeping track of everything that we went wrong and what we learned from that. This was put into I put it into a contingency planning document in kind of in a form that was oriented to say, if this happens again, this is what you do about it. And here's things that we haven't had go wrong, but could, and this is what you do about those as well. But it was intended with that idea of lessons learned. I don't think that any single source has been put together for that. That is a real tragedy of this thing, but it's also something that I could see is a perfectly natural effect of the continually extended mission that we have had. Remember, the original mission was 4 years long. One team could handle all of that 4 years and could monitor it. They could remember what had happened. And then we extended it for 5 years to get onto Uranus. And that was still the same team or people that had learned directly from those original people. And then Neptune was 3 years longer. And then we had this interstellar mission, which is usually 5 years, and just kept getting on and on and on. At some point there, we kind of looked back and said, well, should have been keeping track of this stuff, but we haven't been, because JPL's kind of modus operandi with previous missions that lasted hours to days and maybe months was you'd have one team go in, build, test, launch, and run the spacecraft. Mission's over, you go on and do your next thing. So these kinds of lessons learned really weren't necessary as far as that program. And it's one of my biggest concerns that the project doesn't really have that looking ahead, because right now they are down to having 3 engineers on the project that have experience that goes back to the prime mission. Everybody else has moved on, myself included. And these people are going to be retiring in the next year to 3 years. What's going to happen after that? I don't know. I have concerns about that, to be honest with you.
Now, as a related question, do you ever get a chance to go up on lab and visit the kids now running the mission? If so, what is that like?
I have not had that opportunity, and I'll just kind of leave it at that.
Okay. Sure. So the next question is, if we so desire, can the Voyagers be brought back to Earth?
Absolutely not. They're going away from the Earth at 1 million miles per day. That's really fast, 40,000 miles an hour. To slow those down, turn them around and coming back would take the gravity of a planet much bigger than Jupiter. They'd have to swing around and come on back in. The amount of propellant on board would never allow them to be turned around, and there's no reason to. They are going to be operating and making gathering data as long as they possibly can. We want that to happen. You might envision that if we brought them back, we'd get into this Voyager 6 scenario that Star Trek once projected in one of their movies. So let's not do that.
Raisa, before the next question, we had the tickets for the posters that are up on the board. If anybody didn't have a chance to pick them up above, I'd be happy to give them to you while he goes on with the question and answer session.
Yeah, very good. Thank you.
Okay.
I will say, as far as these posters, these are Voyager collectible posters from Neptune that we just came into my hands at one time, was out of a trash can, basically. And they are the property of Western Amateur Astronomers. So it's the good graces of WAA to be able to provide these for us tonight. And it gets them out of my garage. Should we start questions here, or do you want to continue on?
I have like 2 more questions, and then we could go to the in-person audience. We hear a lot about the contribution of the space industry to daily lives, the technologies that were developed for space, and then they found their way in our daily lives. You did mention about the data compression algorithm. Is that one of them, or is that just something that stays with the Voyagers?
I don't think that was unique to Voyagers, that particular one, because that is a well-known mathematical thing that could be done. It's simply we realized that Voyager could use that technique. As far as any particular technologies that were developed for Voyager that have found their way into everyday life, I'd have to think about that. I'm not aware of any specific ones like that.
Okay, thank you. And the last question I have from online audience is a scientific question about Saturn's rings. Are they disappearing?
No, not really. Maybe in some very long period of time they might, but for the foreseeable future, there's really no changes on them. The Cassini mission looked at that sort of thing a little bit more closely than Voyager. And if they did find some indication that the rings were changing in a way that might cause their eventual demise, I just don't happen to have that information.
Thank you. We do have more questions, but let's go to the in-person audience. You might need to repeat the questions, though, for us to hear.
I will. Okay, right here.
What can you tell us about the computers on board? I've been programming computers since 1960, and there were 4K and 8K memories. Were they 8 bits, or were they 16 bits or 18 bits?
Yeah. The question was a little more detail on the flight computers, and you might have noticed, I didn't mention it, that the memories were 4K and 8K, 4K for the attitude control and command and control, and 8K for the flight data. And so from a programmer's perspective, I'll just try to answer that. These were 4K computers are 16-bit, and the 8K computer is a 18-bit computer. Those ones that were the 16-bit are plated wire memories, and the CMOS memory for the 18-bit computers. And they use machine language, basically, in order to be very, very efficient with that.
Were they basically like EDP-15s or?
They were special purpose computers, specially built for space missions, and they were the same computers that were used on the Viking mission beforehand. That's what they were originally designed for. Yeah. Another question here. Anybody? Yeah, up here, Ellen. What caused them was the fact that Triton is in a retrograde orbit around Neptune. It was probably a captured object at some time. Retrograde meaning it goes opposite to the direction that you would expect it to go. The direction that the planet rotates is the normal direction. All the other satellites go in that normal direction. And Triton is going in a retrograde direction and in a highly elliptical orbit. That means that it's getting squashed by the gravities. It's very high tidal forces. So internally, Triton is much warmer than it would be on the surface. And so what that allows is at this very low temperature, internally, it can still cause nitrogen to evaporate and under some pressure and be squirted out of these little holes, little surface effects. Okay.
Okay, we have a question from online audience if there's a chance.
Here, John.
There was some discussion years ago whether in fact heliopause was in fact moving back and forth, and we're not clearly clear of it. And in retrospect, was that in fact an instrumentation issue, or was in fact were you in fact measuring the oscillation?
We weren't measuring the oscillation. The question was whether the heliopause is expanding and contracting and basically pulsating. And there's a little slide, I don't know, maybe I can find it here, that actually demonstrates that. And let's see where my mouse is. Yeah, right here. Let's see if we can get this video to play. Well, maybe not. Yeah, that's basically the effect that you're talking about there. And this is has a variation that varies with the solar sunspot cycle, the 11-year cycle of the sun, and it causes this is a theoretical thing, not measured, of course. But yes, the heliopause does pulsate in and out. It may have been the reason why Voyager 1 was 6 years earlier than Voyager 2, even though there's not that much difference in the distance between them. So yeah, that's the case.
Voyager 1 passed through the heliopause more than once.
Oh, I'm sorry about that. Sneezeroo. You got that one on tape. So Voyager 1, the comment here was that Voyager 1 passed through the heliopause more than once, and that was the case. The final time was the time they actually decided this is really it. That may have been due to this pulsating effect. It might have been just because of a irregular surface of the edge, and it was kind of in and out on this kind of a jagged edge. No way of knowing when you only got 2 data points. Okay, anybody else from the audience before I turn it back over to Riza? Yeah.
You mentioned that the aircraft is correct. What causes the aircraft?
Oh, well,
What was the question?
the question is what causes the position or the attitude, the orientation of the spacecraft to change? Why doesn't it just stay in one place? And the reason is you're in space completely free of any kind of friction at all. And so unless you have an absolutely still spacecraft, I mean, absolute down to, absolute zero, if you will, then it's going to slowly drift off, and it could be a little more fast or a little slower. And so anything you've got out in space is going to move unless it's gravitationally bound to stay in one orientation. For example, the moon is gravitationally bound to always face the Earth. But if you don't have that kind of a thing, it's basically there's going to be small movements. We're talking about a less than 1/100th of a degree per hour of rotation that maintains that kind of orientation. But it has to do those every hour or so, it'll start moving outside of the allowed limit, and they just little puff of hydrazine will bring it back in. That's how that happens.
The computer is tape, right?
The what?
The computer inside the spacecraft.
Tape?
Yeah.
No.
So it shakes a little bit.
No, we have a tape recorder that records science data. When that moves, then yes, it does disturb the spacecraft. And in fact, there is one other effect. The RTGs are very hot. They're about 300 degrees centigrade, radiating heat all over, uniformly out. But part of that heat impinges on part of the spacecraft structure. And so there's small non-gravitational accelerations always being impinged on the spacecraft by the RTGs. Solar pressure did the same thing when it was back near the sun.
Passive louvers also contribute to function.
What?
Passive louvers.
Those louvers, I'm not sure we've ever measured that, whether they were balanced enough to not do that. But the louvers have been closed since on their way to Jupiter. I think near Earth was the only time those louvers were open. Okay, any more before I turn it back to Risa? All right, Risa, let's see what else you got here.
Yeah, so you did mention that the Voyager spacecraft were able to verify existence of heliopause and heliosheaths. What about the Oort cloud? And are they now considered out of the Oort cloud, or they're still in?
No, the spacecraft are at the outer edge of what's considered very loosely the Hubble, or the what's that? The cloud that's in by the outer asteroids. The Kuiper Belt, yeah. It's outside of the Kuiper Belt, but just barely outside of that. The Oort cloud, as I said, Voyager 1 is 160 AU away. The Oort cloud is postulated to go out as far as 50,000 AU, or maybe even as near as halfway to the nearest star, since these objects out there are very loosely attached to the sun by gravity. So that is far, 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 far beyond Voyager's distance in any conceivable amount.
Thank you. And you mentioned about the record and the plaque that is on the spacecraft. The question is, why is it made of gold? Why not something else?
Well, it is. I don't think it is made of solid gold. I think it is actually gold plated or gold covered in some fashion, thicker than plating. And the reason I don't know, actually, I've never been asked that question, and I can't really give a good answer.
Well, I have my speculations. Gold is very non-reactive, although it's very soft. So non-reactivity might be a thing, although in space.
In space, there's nothing to react with.
React with, yeah.
Yeah, I can't really say. But as I say, it's not solid gold. There's no reason for doing that. I think, yeah, I don't even want to speculate there. Can't say.
Okay, sure. Thank you. This is it for all the online questions. Are there any more in person?
One more from our programmer.
Is it a 78 RPM, 33 RPM? Or is it?
Well, it's actually, the question is it, what speed does that record to be played at? And the fact is, it is a video disc. It's not really an LP. And so it might be at a standard video disc speed, which I don't know what those are, the video discs that were being made in those days. But it's a question that I have not considered. Okay, last chance.
I'd like to make a follow-up on Saturn's ring,
Yeah,
because they should be unstable. They are stabilized by the shepherd moons discovered by Voyager.
Right.
That's why the rings of Saturn are still there. Without them, the rings of Saturn would disappear. Somebody was asking earlier about are they
Right.
disappearing? Well,
Yeah.
not that we can see, as you say, but that's
Yeah.
why.
and the comment that Tim Thompson made was about the rings of Saturn and their stability. The stability is owed to some shepherding satellites that Voyager discovered at Saturn, and so they are kept in that stable position. But dynamically, they are unstable. So one could expect that eventually they would fall apart.
And now there is one other question regarding the future missions or maybe current missions of NASA. Is there anything interstellar like Voyager? Are they converting any current spacecraft into something that can go interstellar?
The spacecraft that would go interstellar have to be designed that way to start. They have to have been planned to be on escape velocity trajectories from the solar system, going fast enough that they will escape from the sun and never come back by the pull of gravity. The only other spacecraft that are in that configuration are for active spacecraft with the New Horizons spacecraft that went to Pluto, and the Pioneers 10 and 11 are also on interstellar trajectories, but I don't think there's, and they have records on board too. That's just something that wasn't part of my discussion here. So I think those are the only interstellar spacecraft, is the New Horizons and the Pioneers 10 and 11, along with the Voyagers.
People try to stop the Pioneers.
I won't repeat that. Okay, anything else, or are we done here? We've got a drawing to do, these posters. I've got 3 up here. The sets we're giving away are 4 of them. I just happen to have an extra. And it's unfortunately, I can't offer that to the online audience, but at least for the people who took the effort to come here, there's a chance to own a collectible set of Voyager Neptune posters that you might like yourself. You might find somebody that you'd like to gift them to, or perhaps you can make a killing on eBay selling them. So are we signing off, or what happens here?
Yes, I think we could end the online part. I would like to thank everybody for attending. Also, very nice to see some of you in person, virtually. Let me remind everybody that you could see all the events that we have planned on our calendar at ocastronomers.org. And I would like to thank everybody again for joining us and wish everybody great times ahead.
And thank you, Reza, for putting this together.
Sure. So we're signing off online, and you guys enjoy your raffle there. Thank you. Bye-bye.